Today we will study one of the most important rearrangement reactions in organic chemistry, and it is named after the scientist Fries and is popularly known as Fries rearrangement. Now, the reaction can be presented as this is ester of phenol. You see here CH3CO, this is the acid part and it comes from ethanoic acid, and this is the alcohol part, here it is phenol. So this is an ester and it will be named as phenyl acetate. We have discussed in previous videos how to name an ester. The name of the alcohol part comes first and it ends with the acid part, and it ends up in the term ate to represent the ester. Now when we treat this phenyl acetate with a Lewis acid, for example AlCl3, then we get two products. Actually, this is a parallel reaction. In this rearrangement reaction, we have this acetyl group to get transferred to the ortho and para positions, and the electrophilic aromatic substitution that occurs releases H plus ions from the substituted site and it gets attached to the oxygen atom and it gives phenol, a derivative of phenol. Now this is the main functional group most prior between these two. So it will be named as acetophenone. This one CH3CO and this is the phenyl group and this is ketone. So it is acetophenone. But in acetophenone we have one hydroxy group at the ortho position. So we should write here orthohydroxy acetophenone. So this will be parahydroxy acetophenone. Now, one beauty of this reaction is, and one important observation, rather I should say, that this is the major product when high temperature is taken. When high temperature is taken, the ortho isomer becomes the major product, but at room temperature or low temperature, this para-hydroxy acetophenone, that is the para isomer, it becomes the major product. So this is the Fries rearrangement, and I will come to the mechanism now. If someone asks that how to get this molecule, so if you start from phenol, then we have to perform these reactions. First you apply here sodium hydroxide, so it will give you sodium phenate. It is an acid base reaction. You get the salt upon neutralization, and then if you apply here acetyl chloride, then this O minus will carry out substitution reaction here. First this pi bond will come here, then it will again get back to its position, then Cl minus will be released. So we have here it is O, then it is connected to carbon and it is the acyl group, so it will be OCOCH3. In this way, we can derive phenyl acetate or phenyl ethanoate, that is the phenolic ester, from phenol. Now, if you wish to have phenol from benzene, then you can watch my video how to synthesize phenol. There are 5 processes described and you will get it in the playlist alcohol phenol. So in this way you can synthesize the substrate for the Frias rearrangement. But this is not the Frias rearrangement. Frias rearrangement starts with phenyl acetate and it gives you orthohydroxyacetophenone at high temperature and para-hydroxyacetophenone at low temperature. And in any other moderate temperature, it will give a substantial amount of both these isomers. Now, what about the mechanism? Now, AlCl3 is a Lewis acid and it is electron deficient. It is in search of one lone pair. Now, this is sp2 oxygen, this is sp3 oxygen, so this lone pair is available on the basis of hybridization. But another thing is that this lone pair is also in resonance with this pi bond and in this with this aromatic ring. So availability of this lone pair is actually greater, but the diffuseness of this orbital is greater. Now AlCl3 will bind with this lone pair also, but this will not come up with the end product. So even if it binds with this one, it will get released and when it binds with the lone pair of this oxygen, it will yield the product. So there is a transfer of lone pair from this phenolic oxygen to AlCl3 and we get the adduct. Here it will be minus, it will be plus, and we have here COCH3. Now this plus will be neutralized by this bond. This bond will open up upon oxygen, so that we have this acyl cation. Now this is an electrophile and this cation is stabilized by this lone pair through resonance. Now this electrophile will carry out the electrophilic aromatic substitution in this ring. Now since the plus charge has been neutralized, so it has lone pair and it will come into the ring through resonance and the ortho and para positions will be activated. Now the aromatic substitution will occur at ortho and para both. Now the ortho position is sterically hindered owing to this group. So this is kinetically unfavored position. This ortho position is kinetically unfavored. Compared to this, the para position is kinetically favored. This H will then be released as H plus so that the ring gets aromaticity again, since aromatic ring is stable and the charge neutralization takes place in this way. We have the pi bond again, so it will be aromatic the acetyl group is substituted at the ortho position, and here we will have this adduct. Now we have H plus here, and this lone pair will attract this H plus and this will be released again. So it acts as the catalyst. It receives a lone pair, it donates a lone pair, so it will remain neutral. So it will be OH, and here we have acetyl group at the ortho position. So it is acetophenone and hydroxy group at the ortho position. So it is ortho-hydroxy acetophenone. So this is the ortho isomer. And in a similar way, there will be a substitution at the para position. Now this proton will be released so that the aromaticity is gained again. And this H plus is again captured by the lone pair of this oxygen, and AlCl3 get released as before, and we will have the para isomer. Owing to the steric repulsion in this position, at the ortho positions, this is kinetically unfavored. But if you notice this product, you will see that it will be able to form a hydrogen bonding, which is intramolecular. Here we have del plus, we have del minus here, del minus here. It will be a hydrogen bonding, and this is 6-membered chelate ring, 1, 2, 3, 4, 5, 6, and it is stable. So this is thermodynamically stable. So you can write here thermodynamically controlled product, but it is kinetically unfavored, means it has a high activation energy. So this must be the product at high temperature. Hence, we have the ortho isomer as the major product only at high temperature. This is the reason, since it is kinetically unfavorable. But here you see this OH and COCH3 cannot engage in this type of intramolecular hydrogen bonding. So it is not thermodynamically controlled product. And here we see that these two groups are at a distant position from each other, so there will be no steric repulsion. So this is kinetically favorable product with activation energy less compared to the previous one. So it will be the major product at low temperature. So this is the kinetically controlled product and is the low temperature major product. This is the Freyr's rearrangement. Now one can also conduct Freyr's rearrangement photophysically, and that is termed as the photo-Freyr's rearrangement. Homolytic fission occurs at this position. So we have this dot is placed here, and this pi bond undergo homolytic fission. So we have a dot here, and this dot, two unpaired electrons will engage in a pi bond. So we have a radical here. And again with this dot, free radical or electron, if this bond breaks, So this will form a pi bond and we have a free radical here. Now this species will connect at these two positions and it will give you the ortho and the para product. And here we get the major product as the para. So it will be this is one electron transfer, so it forms a bond. So we have this product. Now to gain aromaticity, this H plus is released, it comes here. So aromaticity is gained, and what happens? This becomes O minus and it captures this H plus and it becomes the para isomer. So this is the photophase rearrangement.